All right, thank you, everyone. Yeah, my name's Brad, and I work for the University of Waikato, which is a sort of medium-sized university here in New Zealand. And today's talk is going to be about a big project I did last year, which is doing multi-terabit per second SDN networks. So let's get started. So I didn't want to assume too much knowledge, so I'm going to start here with a very simple slide over what a network is, what the internet is. So the point of a network is to get your hosts talking to each other using some kind of application so that you can transmit information. Now, a lot of people will tell you maybe networking is a game of Pokemon where you've got to collect as many different routing protocols or that kind of thing, but this isn't true. And so the way this at the equipment level usually works is we have a bunch of routers which handle IP addresses and switches which know about MAC addresses. So this is in the OSI model, layer 2 and layer 3. So between our routers, we need to exchange routes, so they need to know how to find other parts of the network. And on our switches, they need to know about MAC addresses so that they don't just be a hub and send all traffic to all interfaces. So in a traditional world, we use distributed protocols for this. So each device sort of builds its own view of the world and does this by forming adjacencies with other devices it knows about and exchanging information. So common routing protocols are OSPF, ISIS for your interior, for inside your network. If you're speaking on the internet, using a thing called BGP. And then for forwarding, for L2, there's some various MAC learning stuff that you've got to do. Now, in an SDN world, what we do is we add in a controller that has sort of an oracle view of the network. It sits above everything, and it can, instead of just making a decision per device, we can now make decisions between groups of devices. And so to make this work, we've got to have now an API that lets our controllers talk to our devices. So, what kind of API do we use for this? So we need something that's an open standard that anyone can read and implement. We need more than one vendor to support it so that we can do this with more than one piece of vendor gear. And another key thing is we need to be able to modify the behavior of the device. And we want to do that because we want some level of consistency, and we'll get into that a bit later. So the options at the moment are kind of OpenFlow and P4 runtime, which you may have heard of. P4 runtime is quite new and only just sort of becoming a standard now, so it doesn't have great support yet. But OpenFlow has been around forever. So many different vendor devices support this now, and that's what I'm going to focus the rest of the talk on. And we'll mention and come back to P4 a little bit later on. So some may say at this point, I've heard of this netconf yang thing that I can use. Well, this isn't quite SDN. This is more of like software configured networking. So a netconf model lets us push down and change the configuration of the device using the vendor configuration language. And this is just kind of like a programmatic interface to the CLI. It's not multi-vendor. Different vendors have different ways of using it. They all have different features. And we can't actually change how the device works. We just have to rely on the code from the vendor to make it work. So here's a traditional switch. It's pretty simple. So it has a control plane, which is the brains of the thing. It's usually a small embedded CPU running, these days, Linux is pretty much what's always going to be on there. All your protocols run as little C applications, usually running as root, and they know how to talk down to the forwarding plane. So the forwarding plane is normally some kind of ASIC, or you'll occasionally see FPGAs or network processing units. But it's some kind of faster silicon that can do things with less jitter than a CPU can do, which is what we want when we're dealing with network packets. So the control plane makes some decision based on some kind of protocol, and it pushes it down to the ASIC so that it can make the packets go in the right place. So an SDN switch, and this is the OpenFlow view of the world, we replace that control plane on the switch with a thing called an OpenFlow agent, and then that speaks OpenFlow API over TCP to your control plane, which now runs on a set of servers. And we have a bit more power there, and we have a larger view of the network, so we can make smarter decisions. So how OpenFlow works, you can simply boil it down mostly to, you get rules. So you make a rule, you push it onto the switch, and the switch carries out that rule. So a rule has two parts, a match and an action. The match is on some kind of header inside of the packet. So you might match on, say, an IP address if you want to do routing. You might match on a MAC address if you want to do switching. You can match on TCP ports, UDP ports if you want to start doing like firewalling type things, load balancer or something. And then you have an action associated with that match. And an action could be like drop the packet. It could be output to a port. Or we can use these things called tables to string lots of rules together and compose them into some simple logic, some if-then-else logic. This is the diagram from the OpenFlow spec on how this kind of works. So you get a packet in, you start in table 0 always, which has a set of rules at priority order, and then you sort of move through these tables until you decide what you want to do to the packet. So what controller can we use? So the reason we need a controller is when you get an SDN switch out of the box, it does nothing, it drops all your packets. This isn't ideal unless you're a very security conscious person, because that's a pretty good secure system if you don't forward any packets. So what we need is a controller that is able to re-implement the features we already had. So we've just lost 20 years worth of progress in networking, we've gone to nothing, and then we need to start building this up one by one again. And today, the clue was in the bottom of the slide, we're going to talk about Faucet controller, which is something I work on. So what is Faucet? So we call it a lightweight SDN controller. So it's not some big clustered thing that you've got to run 30 machines on to get it running. It'll run on anything from a Raspberry Pi up to some big server if you want to support lots of hosts. It's using OpenFlow 1.3, so that's just a version of the OpenFlow standard that's quite well used by production switches, and it gives you quite a bit of flexibility, which is nice. We call it production quality because we've used it in production a bunch, and that's what the second half of this talk will be about. We're very, very careful to test everything we can. So we have over 90% unit test coverage. We have integration tests that test about 200 different network scenarios, virtualized, and also on vendor hardware. So a number of vendors that work with us actually run Faucet, the integration tests, as part of their QA release for their firmwares. So this is how we know that when you go and buy a device that is Faucet branded, Faucet compatible or whatever, you know it works with the latest version because that firmware you're running on it has run against our test suite and told the vendor what features work and what features don't. This also means that sort of Faucet, you configure what you want, and then it can program that the same way on every single device that you buy, no matter what vendor it is. And this is quite a powerful thing when you've got it. So, and we do all this by not using any driver code. So a lot of other controllers, they would have a driver shim layer that changes how the OpenFlow comes out depending on which hardware you've got to match the compatibilities. We don't do that. We went to the alternative approach of working directly with hardware manufacturers to make sure they support OpenFlow, the core standard, and we don't use any vendor extensions at all. So we do all the normal layer 2 and layer 3 things, and we're only 10,000 lines of Python at the moment, but so you can either modify that to add new features, or we also have a policy-driven approach to changing the behavior of Faucet if you don't want to write code. So here's kind of how Faucet works. So we actually have 2 controllers in Faucet, so Faucet Engage. Faucet's our read-write controller. It ingests a config file in YAML format, and it composes some OpenFlow rules and pushes them down to your switch. And then Gauge is our read-only controller. It communicates with all your switches on your network and polls periodically for statistics. And the reason why we want that to be a read-only controller is if you have some kind of mistake or bug in your monitoring code, you don't want this to break the internet or the network. So Gauge can go away, disappear, it can break, and nothing will be impacted on the network. So Gauge also takes a config file, and it can spit out to a number of different database backends. So at the moment, we're quite liking Prometheus, but you can also use InfluxDB and flat files. And then once you've got it in Influx or Prometheus, you can use a Grafana or something to make real-time graphs. Faucet itself is quite neat. It also pushes instrumentation of itself to Prometheus. So you can, so we use this a lot in development, but you can use it when you're running your network as well, just to see where all the CPU cycles in Faucet are going. That's how we work out if we need to make some of our loops faster or do some less heavy processing on types of packets. So that's quite cool. There's also an event system, so Faucet can push into, if you've got some kind of security thing, every host it learns, every host it unlearns, new MAC addresses, that kind of thing. It can push to something that can then implement some of your own behavior. For getting routes into it, we use BGP. It's pretty well standardized, and you can do a lot of things with it. So that's how you can connect Faucet into a regular sort of L3 network. So how do you configure Faucet? Yeah, it's YAML. The YAML represents your topology and features, IP addresses, that kind of thing. So here's an example config, a pretty simple one. So we have one VLAN. We give a VLAN ID of 100. You can add some sort of description so that it appears later in Prometheus so you can find it. It keeps it labeled for you. Faucet can have a number of virtual IPs on your network, and this is useful so that you can use Faucet as your next hop. It'll participate in the network, and it can be v4, v6, whatever you want. And then we have a list of DPs, or data paths, and these are your switches. So in this example, we've got switch 1. It's an OpenV switch, a software switch. It's data path identifier 1. It has 2 ports, and you put them on those VLANs. Another key thing to note about Faucet is everything's idempotent. So as long as you give every controller on your network that config, you can configure them on your switches. So you could have 3 controllers, all of the same config file, and you point all your switches to those 3 controllers. And whenever they get a packet to deal with, they're all going to do the same thing because they have the same config. So this is how you do HA without having to do state sharing between all your controllers, which is a disastrous approach that can have disastrous consequences. All right, so now that's the sort of intro and background. Now let's apply this to a real life network, because I think that's why everyone's here. So every year, there's this supercompute conference in the US. It's quite large. Last year was the 30th anniversary. It's sort of like a 14,000 seat conference. And every year they do this crazy thing where they build one of the world's largest temporary networks. So it exists for about a week. And for that conference at the end of last year, we actually deployed Faucet on this network. And yeah, so what is SCinet? So SCinet's the name of the network. That's a photo of my colleague Lance, who was our chief diagram officer. So he was in charge of making this diagram behind him, all by hand. So every line on that diagram is either a 10G, 100G, or 400G link. Each box is a piece of equipment that someone had to look after. And all those red lines along the top are our internet connections. And this year we had 4.02 terabits per second of internet. The capacity of the network internally was a lot larger than that, but that was how much internet we had that we had to deliver to sort of all the booths on the show floor of the conference. So this thing was $52 million of hardware, 4 tons of equipment, 225 people to manage this whole thing. It's big is the one thing to take away from that. So let's take a little step back. So how did we kind of get involved with this? A small SDN controller team in New Zealand, large US conference. Well, we kind of approached their conference committee early last year, and we kind of said, hey, can we help you out with some of your problems? And can you help us by deploying our project and showing it works? And they pretty quickly accepted our proposal, and then we sort of began work. So what does this involve? How do you manage a thing like this? Well, lots and lots of video conferences and to lots of faraway time zones, so a lot of late nights and early mornings. In particular, our team for doing our part of the deployment, we were split between Hamilton, Wellington, Berkeley, Champaign, and Dallas. So it was a lot to manage. But luckily, we had a really good project management team who helped us out there. And so, when you're doing a project, the first thing you do is come up with some scope and some requirements. So they were pretty keen for us to do a parallel with their regular network so that they wouldn't have to have the hassle of learning everything, and we wouldn't have to have the hassle of learning everything they did. So we kind of ran them side by side, and then booths would either be on the regular SCinet or they'd be on the Faucet SCinet. And we managed to get about 25% of the network connected to us. So we would pair with their core routers and advertise and receive routes over BGP. Each booth would be a separate VLAN and subnet, so separate L2 domain, which is quite nice, limits your error, your problem domain. So we had to support booths. They could buy 1 gig internet connections, 10 gig connections, or 100 gig connections. Yes, that's right. For this conference in the middle of Dallas, to your little square booth, you could get 100 gigabit of internet for a reasonable price. It was quite nice. And then they have this kind of customer information database built in Django, which tracks every order, all the connection information, and we just need to integrate with that to learn everything. So we kind of started by sketching this rough diagram. It took us about a month to get to this point. This is very quickly drawn, and I don't even know what it's drawn in. But so we see at the top these 2 core routers, and they wanted us to connect at 200G to each core router. And that was just so that if one of the fiber pairs failed, we'd swap over to using the other one. So we had to use LACP, Link Aggregate Control Protocol, to manage that. And then the middle would have some kind of router. So I guess I need to introduce some terminology. So they use the terms NOC and DNOC. So a NOC is, normally you'd say Network Operations Center. Well, they tie that into the core of their network. So wherever you see NOC, just read core. And then DNOC stands for Distributed NOC. And those are the sort of access bits of the network, and they are all across the show floor. So you've got to, physically be in lots of different places. So Faucet would be in each DNOC, so 5 of them, and booths go into a DNOC. And then the DNOC would carry up to the NOC router, and then that would go off to the internet. So we kind of did things backwards, I guess. We have a design, but no equipment to put on the network. So what you do at this stage is you call some people, and you ask for some favors very nicely. Brilliant thank you to LA Telesis, Cisco, and NoviFlow, who all donated us, loaned us for the project duration, which was about 8 months, 2 devices of 100G. Once they sort of told us what they were going to give us, and we sort of organized shipping to get to a test lab in Berkeley, because we kind of wanted to assemble the network before we took it to the show, just to make sure everything worked. So that's what we did. And this involves a lot of waiting, so we had equipment come from Canada, various states in the US, and you got to kind of wait a little while for this to appear physically where we wanted it. So while we did that, we did a bit of design, now that we actually know what equipment we're going to get. So this is kind of what we ended up with in the end. So our network had 75 100G ports, 146 10G ports, and 48 1G ports. I would have loved to have used them all, but there simply weren't enough people and booths to actually use that much. But yeah, if this thing was fully configured, it would be 9 terabits per second, which I think is one of the larger OpenFlow deployments out there. I'd love to be proven wrong, though. So the network's pretty simple. So in the middle, we had a barefoot Tofino ASIC running inside a switch provided by NoviFlow. And this did 32 ports of 100G, and it's a P4 capable ASIC, which we'll talk about soon. And then off to the side here, we have our controller, and then we have this 10G, what we call an NFV link. So NFV is Network Function Virtualization. And all that means is instead of a network function living on a switch or a router, like DHCP, BGP, that kind of thing, you pull it off, run it on a Linux box, use ISC DHCP server or Bird or something, that's about all that means. And then we go through this like blue DCI layer. All that means is data center interconnect. It's an optical transport network. So when you've got these sort of DNOCs and NOCs they've got one NOC and then all these DNOCs all over the show, you don't really want to run hundreds of pairs of fiber to all these places. So they brought in a bunch of optical gear so that it muxes a bunch of different colors of light onto one pair of fiber, which can then be broken out, which makes things a lot easier. And then these are the models we used in each DNOC, and they all had varying numbers of 10Gs, 1Gs, and 25Gs, 40Gs, and 100Gs. There's a lot of different ports. So yeah, Faucet, it would handle the VLANs. It did V6 router advertisements to give out IP addresses. It did inter-VLAN routing, so a lot of the booths wanted to do demonstrations where they did large file transfers at high speed between different people on the show floor. So you have to make sure that you can route between the booths. So that's what the inter-VLAN routing feature let us did. And then we implemented a bunch of network security policy at the bottom of the network on the access ports. And that's for dropping things like rogue v6 RAs, rogue DHCP servers, that kind of thing. And Faucet lets you easily do that kind of stuff. Then for NFV, we did DHCP and BGP on the Linux box. So yeah, let's talk about this P4 thing. So the way P4 works is a bit different to OpenFlow. So we end up with a P4 program, and that's user supplied, and that defines, so you kind of get this micro C language, and you define what your packets look like, and then how you want to interact with your packets. And they have a match action table sort of system similar to OpenFlow. And then your vendor gives you a P4 architecture model. You munge these together, put them into a P4 compiler that your vendor supplies you, and that spits out a runtime API at the top, which is a control plane, and it spits out a firmware for your switch. So this is how that P4 barefoot switch works. And then on your switch, you end up with some tables and some memories. Now, Faucet doesn't support OpenFlow, but it can talk to this P4 Tofino box. So how did that work? Well, what you can kind of do is you can write OpenFlow, the application and the specification, as a P4 application, and then you can compile it with Barefoot's P4 compiler, load that on their ASIC, and now Faucet can suddenly talk to this box it couldn't talk to before. And a big thank you to Noviflow for writing that for us and making that available so that people can purchase today. So sort of while we're still waiting for our equipment to actually physically turn up, we decided to do a little bit of development back here in New Zealand. So what we did is we'd identified all the features we needed to work, all the functionality, and we added integration tests to our integration test suite to verify that all these features worked how we thought they worked. And we set that into the integration test system. And that runs on every single commit that comes into our GitHub. So that was our sort of way of making sure this never broke, because we tend to change code quite frequently and refactor a lot. So it's nice to know that those integration tests are there and constantly running so that we can't break things that were already working. We also built a scale model at my workplace, WAND, at University of Waikato. So the nice thing about OpenFlow and Faucet is I grabbed a whole bunch of random devices from different vendors than we were using on the show floor, different models, different port counts. But you can build the same topology, you can boot it up, use the same configs, and it'll work exactly the same as it did to the big one. So that was quite useful so that we could sort of see things working before we actually built our test lab on the real equipment. And then we started to work on the automation. So automation is really great for networking. So automation lets you define a set of tasks once, and you can infinitely carry that out for no cost, which is absolutely brilliant. Applies perfectly to network service definitions. So if you've got a bunch of ways of handling customers, you throw this into automation, and you can just spit this out every time a new customer comes. So we used Ansible in particular heavily for our deployment to make our lives a lot easier. And the way this worked is, so we ended up with, so we got the customer database, which was the source of truth for the network, so it knew everything. And then I wrote a little Python script, which used the Django models of their customer database to it just blindly dumped everything from Django into a YAML config file, data structure thing. And so you end up after this with about 300 lines of YAML. And then I used that as a variable input into Ansible to sort of, I could then look that up when I built my templates. So in Ansible, you kind of get like Ginger templates, which you use a bunch of variables, and you can do substitution and for loops to output a sort of final version. And so I wrote, in the end, about 180 lines of Ansible, 260 lines of Ginger templating, and you sort of combine these together, and out at the end pops all your configs, so over 1,200 lines. And so you can sort of see the ramp up here. You do a little bit of work, but at the end, your automation does everything for you. And this is kind of all available online. I don't know how useful it is, but it's there if you want to have a look at writing Ansible for networking. And I also put up all the generated Faucet configs if people want an example of how you run a huge Faucet network. But hey, things arrived. That's exciting. So when all these sort of boxes turned up, we had to kind of like build the lab. And in particular, I'd like to give a shout out to Allied Telesis here, who they went into their lab in San Jose. They grabbed a bunch of switches out of their lab. They put them in a car. They drove that car across the Bay Area to Berkeley. They hand installed all of our devices for us and then asked, hey, what else can we do? I see they're also a sponsor of this conference, and I'd just like to shout out Allied Telesis in particular. So when we had everything sort of labbed up and plugged in and fibers everywhere, so we'd already kind of got the Ansible, so you just hit go on the Ansible, it deploys the network, and then the trick is to throw a lot of traffic at it. And what I've found is network namespaces are fantastic for this. They're extremely lightweight in Linux and easy to spin up thousands on a single box. So I had a bunch of 10G test hosts, and on each I spun up about 1,500 test hosts, network namespaces. And so a network namespace effectively represented like a booth at the conference. So the conference only had, in the hundreds of booths, but we like to be a bit play on the safer side, so we spun up a factor of maybe 10 over what we needed. And then I wrote a couple of random bash scripts to manage all my network namespaces because they're a bit hard to manage by hand. So I had this on-all script, and it just knew how to log into every network namespace and run a command. And you could have like a ping-all script that knew how to ping every network namespace. And so you just run that in the background to make sure you've got good connectivity, because they would report when they had a connection failure. And then I had this random iperf test that you ran it. It found a random pair of hosts on the network and did an iperf and made sure it was 10G. Now, unfortunately, I didn't have any 100G test equipment, so I couldn't actually test it at full speed. But you kind of just assume that vendors know how to make fast network hardware. And so after a couple of weeks of testing, making sure everything was happy, we shipped it off to Dallas for the conference proper. And how this kind of starts is it starts with staging. So this network is made by 225 people, all working on different teams and different projects. And staging is the first time where these all come together and we see if what everyone's built over the year has worked. So it's quite a tense sort of time when things don't work. And the other interesting thing is the whole network's built off-site. Not really off-site, but in a different place to the show floor. So yeah, this is when a lot of sort of the interrupt testing and diagnosing of problems happened. And this is a photo of a portion of our team after we booted up our thing for the first time and had no issues. And you'll see in the background here, this is the network and all of the different cabinets. So we're pretty excited about that. And then this is kind of the show floor. This is half of the show floor. And so that staging network is sort of out in a different part of the building. And then all the carpet layers start doing their thing, start to build the conference. You'll see aisle markers in the roof there, and that's to designate a sort of walking aisle between everywhere. You'll see some yellow taped things to the floor. Those are fibers and powers. So as they're building the show floor, they're actually doing a lot of underfloor fibers to each booth, which turns out to be annoying when someone sort of runs a tractor over it and breaks it. But that's all right. There was a whole team of maybe 20 fiber people who just went around resplicing and testing fibers. Did not envy their job, I have to say. And then, $50 million worth of equipment. The last thing you kind of want to see is fall off a forklift, but there is the option of that happening. But luckily, our forklift operators were very, very smart and safe, and we safely got the network sort of forklifted in. And now I can say that I've done a network load by forklift. I haven't really deployed a network like that before. And then once it's gone from the staging area to the show floor, we can now fill in all the production information. So connections are still coming in right up until the last sort of week before the conference. And there's kind of a point where they say, no more, you cannot buy any more connections. You should have done that ages ago. And then that's when they sort of tapped us on the shoulder and said, hey, you can pull from our database now, all your connection information's there. And so this is my colleague Josh hitting go on Ansible, and then that automatically spun up the whole network for us. So it went from its testing config to the real config. And then after you do this, you kind of have to just work with booths as they get built to ensure that, that each connection sort of comes up and works. So this is what a DNOC looks like. So it's like a little mini booth, all behind predictive wall. And then that's the rack that's inside of it. So at the top is the regular SCinet switch. Then we'd have a Faucet switch in each DNOC. And then there's the optical transport layer at the bottom, which is some pretty serious gear. And then there'll be aerial fibers in from the NOC, and then ground fibers to each booth. And so in here is a huge patch panel where you kind of patch each cable, and there's a team of people that do all the patching for you. And this is what the NOC looks like. So behind here is where all the operators sit for the duration of the conference to monitor and check for problems. And then they kind of put this Perspex wall on it so people can come and look at all the blinky lights, because that's how you know a network's working, if the lights are blinking the right amount. Now, because we hadn't seen 100G work before, and some of the booths took a little while to get built, you know, what's there to do when you got 225 of the brightest networking people in the country? You go around and tap people on shoulders and ask who's got 100G in their laptop. Turns out no one had it in a laptop, but someone had it in a form factor like this with a handle on top. And so we just put these in different DNOCs and then ran iPerf to test that everything worked. And you'll see that our spikes go nicely up to 100 Gbit. So we were pretty stoked by that. Now this was meant to be a continuous iPerf, but you might notice there's some gaps. We found a lot of flaws in their config on their Linux boxes that meant iPerf would crash every few minutes. So our network broke their stuff. So we were happy we weren't the ones breaking. And so then you come to showtime, and showtime is the least stressful part of the whole thing because you've done all your testing, everything's working. So all you pretty much do is watch for tickets coming in. You do a lot of walking around, talking to people, trying to get as much swag as you can. We did a lot of monitoring for this network. So Faucet gives you good visibility of the network. So we had a Prometheus running with Alert Manager, and we defined about 10 different alerts that would tell us if something serious happened. I'm happy to report we didn't get a single page throughout the whole thing. And then sort of the tickets are usually pretty simple things, like a lot of fibers. So fibers are a pair, a TX and RX, transmit, receive. A lot of times these get flipped around, and then you've got two TXs going into each other and two RXs going into each other. You just got to roll the fiber so the link comes up. Everything on the network was meant to be single mode optics. A lot of booths brought multi-mode optics, and that doesn't really work when they're at different frequencies. So you'd go and put a fiber optic in, and they'd be happy. A lot of light meters and OFTDRs to check where fiber breaks were. Unfortunately, we had quite a few booths that did have those kind of problems. And then everything's done, clean up. So we spent 7 months planning this thing, 3 weeks testing it, 3 weeks setting it up, and it all goes away in one day. And that is a very chaotic day, I will tell you. So what did we learn from all this? So it's always nice to reflect on what worked well and what didn't work well. So the feedback we got from the people that do this every year is they liked that we could automate sort of the common use cases. So they have some amount of automation, and it kind of works, but sometimes there's a little bit of problems with it. And 90% of customers are pretty boring. They just want internet. But there is the last 10% that do want something special. So a lot of them bring in WAN links from other continents, other parts of the country at very high speeds, and they want to do show-off demos and that kind of thing. It is a supercompute conference after all. People are trying to sell high-speed storage and clusters, so they want to kind of prove that this kind of works. And so by automating that easy 90%, the operations team could then spend their time actually on these more interesting things, which gave them a bit more satisfaction. Faucet also allowed us to effectively ignore the underlying network equipment. You could have, on that last day, before the conference were ready to go, you could have given us another box from another vendor and swapped them out, and it all would have worked pretty much exactly the same. And in fact, we kind of had this. So we started the network with 5 devices when we needed 6. And one of the vendors ponied up and supplied that last switch like a week before the conference. You just slide it in, the automation gets told about it, and then it starts building circuits onto it, which is quite nice. And yeah, ultimately, the last thing to take away from this is we proved that 10,000 lines of Python written in New Zealand can easily handle 9 terabits per second. So there's a photo of most of the team that did the Faucet deployment, and I'd like to thank them so much because it was a real joy to work with them, and we did a lot of cool things, I think. And if you are interested in Faucet, you think it might be able to help you, our website has mailing lists, GitHub, documentations. Tomorrow, in fact, I'm actually running a tutorial where we start with a blank Ubuntu box, and we go all the way through to implementing a somewhat complicated Faucet network virtually on your machine. So that's going to be in A3 tomorrow afternoon. If you want to hear about our crazy deployments, I'm sure there'll be more. I usually post them all to our Twitter. And then finally, I think I've got some time for questions. That's, of course, every network operator for the conference taking a photo in front of the NOC. And you'll see behind, that's kind of the area where we're all working from. So can I take any questions? I'll put the slides up on my Twitter as well. At the back, I think we've got a microphone. I can repeat. What do you want to do?
Hi, going back to the photos that you had a picture of the rack with the hardware in it. There's the details of what hardware that photo there. There's the details of what hardware the Faucet switch is anywhere.
So, those are all the model numbers. And if you go to the Faucet documentation page, there's a vendor section where our vendors publish which devices you can buy with support. But generally, so AT, pretty much all of their sort of X930, X950, X510, and actually a lot of their X series support it. Cisco supports it on every Catalyst 9K device. HP supports it on all their Aruba switches. NoviFlow supports it on every switch, and then there's another couple of vendors we're trying to onboard at the moment. So there's about 4 or 6 vendors you can use at the moment. But come and see me if you want more details, and I can get you in touch with any of our hardware partners.
So you mentioned at the beginning that the SDN controller can participate in the network itself. When would you do that? Why would you do that?
Why would you do it? So you want to use it as your router. And the reason why you want to do that is because routing's good. But no. So how the routing in Faucet works is so you can use DHCP or IPv6 router reversements to tell client devices that you are an X-top. And then they need to be able to resolve your MAC address. So you need to do ARP and IPv6 neighborhood discovery to be able to respond to them. And then Faucet has a routing table. It builds a fib. It puts that on the switch. And then as packets come through with the Faucet IP and Faucet MAC on them, we do all the routing in hardware on the device so that you get line rate. And it's basically just you can think of it as an NFV. So instead of the switch or router itself responding to neighborhood discovery and having an IP address on it, we have it in our control plane in our controller machine, and it sort of puts enough config down with OpenFlow so that it actually still all the routing happens on the switch. If that makes sense.
Any more questions? Okay. In that case,
One more.
Most of the switches that Faucet is sort of configuring and then managing, operating in a hybrid style mode for learning like remote Macs and stuff like that, or do they basically ping the first thing in every flow up to the controller to figure out
So
discovery?
So how Faucet works is we want you to put every device in pure OpenFlow mode where it does absolutely nothing. There are a lot of different hybrid solutions. We get some parts happen on the switch, some parts happen in the controller. We prefer to do everything in the controller because it gives us more, well, control. How does the switching work? So, well, how does, I guess, everything work? So we do a mixture of proactive and reactive. So we put down as many flows as we can when we start up, so that pretty much not much goes to controller. So we very heavily, severely limit what goes to the control plane. If we don't have to, we won't send it. We also truncate every packet that goes to the control plane to not overload it. And then when we do finally have a packet that has to go to the control plane, maybe it's because it needs to do neighborhood discovery, maybe it's because it's a protocol offload that Faucet needs to receive, we will learn as much as we can from every packet that gets sent to us. So we'll take the small number of bytes that we've copied up to the control plane, and we'll ring out every little piece of information we can and store that. So this is how our Mac learning works as well. So by default, and you can change this, we have a lot of different flooding modes. By default, Faucet will put rules down that make a VLAN flood group, and the packet, when it first receives it, sends it to that VLAN flood group, so everyone gets the packet, and then we copy one copy up to the control plane, we learn it, and we push down the learn rule. So Faucet tries to be very smart about how it handles the control plane.
Any more questions?
Yeah, people keep telling we should write a paper, but we haven't quite got around to it yet. So the question for people who didn't hear, is it documented, our learning optimizations? So we've spent probably 2 years. So we spent like 3 years building Faucet, and then we spent the last 2 years optimizing it and adding features. And at this point, we've probably put about 2 months into L2 and L3 optimizations. And this is how we can get away with using Python to run a huge network. You'd never think it would be possible with the global interpreter lock, but it turns out if you do things smart in Python, there's a lot you can do. And mostly it's just documented in our code, unfortunately. We have a little bit in pieces in our documentation, but yeah, we really should write a paper on benchmarking Faucet, because there's a lot of cool stuff we do. I could do another whole talk on that. Yes?
I was just wondering about how the network switches themselves are bootstrapped to talk back to the controller in the first place.
Okay, so you'll see there's a control plane network. It's all out of band.
So are they, do they assign addresses on that control plane network themselves?
Yeah.
So just DHCP or something?
Yeah, most of the places where we're using Faucet, you kind of want the out-of-band network management thing, so you can SSH to them, you can pull configs off them, whatever. And it just happens you can run OpenFlow over this as well. There's some tricks you can do in OpenFlow with in-plane control. It's a little trickier though, because you have the bootstrapping problem, but there's some approaches you can use to make that less problematic.
Okay, so we'll call that a day then. We'll, to allow time for people to move, let's show our appreciation to Brad.
Thank you, everyone.